Good morning students. Today we are going to see the first experiment in physics laboratory, that is to determine the Young's modulus of a given material of a beam using uniform bending of a beam method. Okay. Now before that we must know what is a beam. A beam is a rectangular bar or a cylindrical rod whose length is very large compared to its thickness, and it is made up of homogeneous and isotropic material, and its area of cross section is uniform throughout its length. So here according to the definition for beam, this 1 meter scale will act as a beam in this experiment, and we are going to determine the Young's modulus of the material of the beam. So this is a wooden scale, so we are going to find the Young's modulus of wood. If it is a steel, if this rectangular bar is made up of steel, you are going to find the Young's modulus of a steel. Now, what do you mean by Young's modulus? It is the ratio, it is one of the elastic constant from which you are going to find the mechanical strength of any material. How much stress a material can withstand, that can be determined by finding these elastic constant. There is not only this Young's modulus, there is rigidity modulus, bulk modulus, like the different elastic constants are there. From that you can determine the strength of the material. Now Young's modulus is the ratio between the longitudinal stress to the longitudinal strain. What is longitudinal stress means? It is force applied per unit area along the length of the beam, which is measured by the unit Newton per meter square. What is longitudinal strain? Strain means it is change in length to the original length. So when you find the Young's modulus capital Y is equal to longitudinal stress by longitudinal strain, then you will get F by A, force per unit area, divided by change in length by original length. So you will get F capital L divided by A into small l. So the unit will be for Young's modulus of the material is same as that of the stress, that is Newton per meter square. Okay, now we will go for the method of this experiment. Now what is non-uniform bending of a beam? See, you can bend a beam in two methods. One is uniform bending of a beam and another is non-uniform bending of a beam. In uniform bending of a beam, we will apply load at 2 points along the length of the beam. Along the length of the beam, at 2 points when you apply a load, the beam will bend like this. This arc of bending of a beam, when you extend, it will describe a circle. That is, the radius of curvature throughout the arc of the bending of the beam remains constant. But when you go for a non-uniform bending of a beam, we will apply load only at 1 point along the length of the beam, either at the center or at the free end. One end will be fixed, the other end when you apply load, then the beam will bend like this. This is an example for cantilever. This is just for your information, but see, suppose in non-uniform bending of a beam, when you apply load at the center point, the beam will bend like this. When you extend this arc of bending, it will never describe a circle. The radius of curvature will no more be constant throughout the arc of the bending. That is non-uniform bending method. So there are two methods to describe the to find the Young's modulus of a material of a beam. One is uniform bending of beam method and another is non-uniform bending of a method. Today's in your laboratory class, we are going to find the Young's modulus of a given material of a beam by uniform bending of a beam method. Okay, now we will go for the experiment. In this experiment, what are the different parts we are going to use? Different apparatus is, this is a beam. This is a 100 centimeter scale made up of wood. For this wood material only, you are going to find the Young's modulus. In this 100 centimeter scale, exactly at the 50th centimeter, that is at the middle of the beam, a metallic bob is fixed with the help of a candle. We have fixed, and you can see the inverted position of a bob pin, which is fixed exactly at the 50th centimeter, that is the middle of the beam. Then we are having two knife edges. These knife edges are to support the beam. Then this is an instrument called a traveling microscope. You know what is microscope? A microscope means it is a instrument which will magnify and resolve the image of an object. Magnification means a small size object will be magnified several times. It will show big. Resolution means each and every part, each and every point of the object distinctly, separately you can see. So such an instrument is this microscope. Why this microscope is traveling microscope means this traveling microscope has an arrangement such that it can travel horizontally as well as vertically. Now what is horizontal? How it will move horizontally means, see, this is the radial screw for the rapid movement of the microscope in the horizontal direction.
Start.
See, this is the radial screw for the rapid movement of the traveling microscope in the horizontal direction. See, to this microscope, traveling microscope in the horizontal direction, one small scale is fixed. This is called vernier scale. This is vernier scale. It has 50 divisions. It will have 50 divisions. So when you move the traveling microscope in the horizontal direction with this radial screw, there is a small scale attached to the traveling microscope. That small scale is a vernier scale which have 50 divisions. And this is the, along this traveling microscope with the vernier scale, it is moving along the horizontal scale. This scale is the main scale, which is calibrated in centimeters, and each 1 centimeter is divided into 20 main scale division. In this main scale, each 1 centimeter is divided into 20 main scale divisions. So number of divisions in the vernier scale is, this small scale is, in the horizontal direction is 50 divisions. Now the number of division, how the calibration is in the main scale is, each 1 centimeter, it is calibrated in centimeters, and each 1 centimeter is divided into 20 main scale division. Now this radial screw, which is also called as fixing screw, will fix the position of the traveling microscope in the horizontal direction. And in this side way, you are having another, in the side there is another screw called tangential screw. This tangential screw is used for fine adjustment of the microscope movement in the horizontal direction. So this is for fine adjustment. This is also called as tangential screw. So this traveling microscope is moving in a horizontal direction. Now the same traveling microscope can move in the vertical direction also. For vertical direction, this is the tangential screw. Sorry, this is the radial screw or fixing screw. When you release this radial screw, this is the radial screw for the traveling microscope for the movement in vertical direction. So when you release this radial screw, traveling microscope will move freely along the, see, here there is a vertical main scale. Along this vertical main scale, this traveling microscope will move freely when you release this radial screw in the or fixing screw in the vertical direction. Now when, see, this, in this top there is a tangential screw. In this top there is a tangential screw for the vertical movement of the microscope. This is for fine adjustment. So this is the tangential screw. So when the traveling microscope move along the vertical direction in the main scale, this is the vernier scale. This, along with the microscope, a small scale is attached. This is the vernier scale for the traveling microscope in the vertical direction. So this is the vertical main scale, and this is the vertical direction vernier scale. Here also the calibration is same as that of the horizontal scales. That is, vernier scale will have 50 divisions, and in the main scale, each 1 centimeter is divided into 20 main scale divisions. So in both the horizontal scale and the vertical scale of the traveling microscope, the calibration is same. Now another thing I have to tell you, see, when you want to use the tangential screw, that is the fine adjustment screw, this screw or this screw for the horizontal direction, when you want to use this radial screw, their respective radial screw should be in tight position. Then only you can use this fine adjustment screw. Okay. Now about the microscope, you know that microscope means it is a cylindrical, it is used to magnify and resolve the image of an object. It consists of a two cylindrical tube which is coaxially slide over each other. one end of the tube you are having an objective lens to view the object, and another end you are having an eyepiece, so that the eyepiece have a plus shaped crosswire attached to it. And this is the rack and pinion arrangement. See, this is the rack and pinion arrangement to adjust the focal length between the objective lens and eyepiece, so that you will get a clear, magnified, resolved and inverted image of an object. The magnified image of the object will be always in the inverted position in the microscope. So this is the rack and pinion arrangement. See, here there is one screw. This screw will tilt the position of the microscope, but with this screw you have to fix a position of the microscope, so that throughout the experiment this position of the microscope should not change. Okay. Now we will come for this is about the apparatus. Then to measure the thickness and breadth of this beam, because for the calculation for Young's modulus of the material of the beam, the breadth of the beam, this breadth of the beam and the thickness of the beam you have to measure. So to measure the breadth of the beam, you will use Vernier Calipers. This is an instrument called Vernier Calipers, which you have seen in your school and all. So with this we will use to measure the breadth of the beam. How you can measure the breadth of the beam is, see, this is the sliding screw. So between the two jaws, one is a fixed jaw, another is a movable jaw. Between the two jaws, with the help of the screw, you rotate and keep tight it, insert the beam, along the breadth of the beam you insert this Vernier calipers between the scale at the two edges of the scale along breadthwise, and you have to note the main scale and Vernier reading in the Vernier calipers, and you have to measure the breadth of the beam. Like this, at two different positions you have to measure. You should not measure keeping at the edge of the jaw or at the top end of the jaw. Only at the middle position you have to keep the Vernier calipers, and you have to view the readings, keep your face straightly. So at three different positions you have to measure the breadth of the beam. And this is the screw gauge with which you can measure the thickness of the beam. See, it is also having two jaws, one is fixed and another is movable, and this is having a main scale and a pitch scale. Here we want in screw gauge, the Vernier scale is called as pitch scale here. Now you have to find the thickness of the beam using this screw gauge. See, you have to use this screw only and tight it. So that you have to tight it and find the thickness. Just give one gentle click. You should not tight it roughly handling this part. You have to tight the screw gauge with this screw only. So at three different positions you have to measure the thickness of the beam. So the thickness of the beam is measured with the help of a screw gauge, which is in millimeter. So you have to convert it into meter. So 10⁻³ meter you will get the reading. The Vernier calipers, the reading is measured in centimeter. So the breadth of the beam is measured at different parts of along the length of the beam in centimeter, which is measured in centimeter. So you have to convert it into 10⁻² meter. Now about the travelling microscope, the readings I have told you, the main scale reading is measured in centimeters. Each 1 centimeter is 20 main scale division. Means how it is calibrated means 0, 0.05, 0.1, 0.15, 0.2, 0.25, like that. Each division, the value of one main scale division in the main scale of the travelling microscope is such that it is equal to 0.05 centimeter. Then the number of divisions in the Vernier scale is 50 divisions. So least count of a travelling microscope is equal to value of one main scale division divided by number of divisions in the Vernier scale, that is equal to 0.05 centimeter divided by 50, that is equal to 0.001 centimeter. So this is about the travelling microscope reading calibration. Now how to do the experiment? We will see by means of uniform bending of a beam. Even it is a 100 centimeter scale, the length of the beam in this experiment is the distance between these two knife edges. So we have to keep the, for example, in our experiment, let the length of the beam is 60 centimeters. If you keep 60 centimeter means from the middle, we know that the bob pin is kept exactly at the middle of the beam. So from the middle of the beam to left hand side 30 centimeter, to the right hand side 30 centimeter. Like that only you have to adjust the knife edge and keep such that the distance between two knife edge is 60 centimeter. So see, exactly at the 50th centimeter the bob pin is fixed with a candle. So now from there to 20, 50, here this side the scale is increasing means 50 to 80. The knife edge is kept at 80. When the scale which is moving from left to right, it is having 80 centimeter, right to left it is having 20. So two sides scale is there in the beam. So 80, 20 I have kept. So from the middle of the beam, the 50th to 80, this is 30 centimeter. Here I have to keep the knife edge at again 20, 80. There 80, 20, here 20, 80. Now 30, 30. From the 50, from 50 this side 30, 30th centimeter, from here to 50th centimeter to 30th centimeter on this side. The knife edge is at 20th centimeter. From 50th centimeter to right side, the knife edge is at 80th centimeter. So the distance between the two knife edges is 60 centimeter. That is the length, small l of the beam. 60 centimeter is equal to, L is equal to 60 centimeter, that is equal to 60 into 10 to the power of -2 meter. Okay. Now we have to apply a load. How we are going to apply a load means, we have to apply load such that the load should be applied at, because it is a uniform bending of a beam method, we have to apply load at 2 points. How we are along the length of the beam. How we are going to apply the load means, from the knife edge, there are two knife edges. From the two knife edges at equidistant on either side at 2 points we have to apply a load. So here from the knife edge 10 centimeter away, this side I am going to apply a load. From this knife edge again 10 centimeter away I am going to apply load. So this is at the 20th centimeter means I have to apply a load at 10 centimeter. From the knife edge, exactly, knife edge is at 20th centimeter. Now at the 10th centimeter, I have applied a load. The load is of, this is a Dept load. With this hanger, it is 50 grams. Now same equal weight should be, equal mass should be applied here also. So again another 50 gram I am going to apply, again 10 centimeter from this knife edge, that is, this knife edge is at 80th centimeter means now at 90th centimeter I have to apply a load. So at 10 centimeter equidistant from the knife edge, at 2 points along the length of the beam we have applied a load. So this distance between the knife edge and the weight hanger x, small x is equal to 10 centimeter, that is 10 into 10 power minus 2 meter. Now we have applied a load. Now because we have applied a load at 2 points along the length of the beam will elevate like this. This beam which is there without load condition, now because of the load applied it will elevate like this. Now the bob pin which is attached at the middle will elevate over a small distance. That amount of elevation without load in this position, after applying load, this elevated position, we are going to measure with the help of this traveling microscope. Now traveling microscope, where you have to focus is, you have to focus this bob pin, tip of the bob pin. I have already told you the traveling microscope, you will get the inverted image of the magnified resolved object which you are viewing. So this bob pin in the inverted position, it is viewed through the microscope. Now in the eyepiece of the microscope, I have informed you that you are having a what? Crosswire, plus shaped crosswire attached to it. So I will focus this microscope and adjust this rack and pinion arrangement. I have told you the position of the microscope you should not change, but adjusting this rack and pinion arrangement, you have to focus that pin tip. Let me go to the board and we will see what will happen, how to take reading. See, I am adjusting this rack and pinion arrangement and this tangential screws, tangential screw, radial screw, and this tangential screw in the vertical direction and radial screw, and adjust all these things, and I am making the tip of the pin, bob pin, it is in this position. Now it is in the inverted position. So this pin tip I am going to coincide with the horizontal line of the crossfire, and that position only you have to note that reading in the vertical scale. Now you can see.
Start.
See, now through the microscope we have seen, you have seen, we have focused, when you see the video you have seen that this vertical and horizontal crosswire wire is there, flush shaped crosswire is there in the eyepiece. Then the bob pin, which is actually when you view the bob pin is in this position. Now through the microscope it is in the inverted position. Now when you see through the microscope, the bob pin which is in the inverted position, we are focused by adjusting that tangential and radial screw in both horizontal and vertical direction, and make this tip of the pin coincide with the horizontal line of the crosswire. See, plus shaped crosswire is there, and that this horizontal line of the crosswire coincides with this pin tip. Like that we have to focus. Once you focus, then in the we have seen the vertical main scale. Now the vertical main scale, which is calibrated in centimeters, and each 1 centimeter is divided into 20 main scale division. In that we are going to take the main scale reading, and the Vernier scale, a small Vernier scale is attached to the microscope when it is moving in vertical direction. So Vernier scale reading and the main scale reading we are going to take. Now how we will take reading, we will see. Suppose I have told you each 1 centimeter is divided into 20 main scale divisions. Suppose this is 12th centimeter and this is 13th centimeter, means which is in centimeter. Now this is divided into 20 main scale division like this. 12 means this is 12.05 centimeter. Then this is 12.1. This is 12.15. This is 12.2. This is 12.25. Like that, each 1 centimeter is divided into 20 main scale division. So, value of 1 main scale division value is equal to 1 by 20 centimeter is equal to 0.05 centimeter. So, like this it is calculated. Now, in the Vernier scale, I have told you it is having 50 division. Now, the 0th division will be like this or with some arrow mark like this. So, let among the 50 divisions, you have to see it is like this. Like that, suppose this is 50th division and this is the 0th division. Suppose this is the main scale. This is Vernier scale. Suppose 0 of the Vernier scale. 0 of the Vernier scale. How to take reading I am going to tell. So the calibration is like this. This is the main scale which is in centimeter. Each 1 centimeter is divided into 20 main scale divisions. And this is the Vernier scale having 50 divisions. How to take reading? Now we have the beam have been applied a load at 2 points and it has elevated. Now when it is elevated, the pin tip also raised. That position we are going to note through the microscope. So in the vertical scale we are going to take reading. How to take reading? Now the elevated position of this pin tip after applying the load, what is its position? We have to note it by noting this vertical scale reading. So 0, how to take reading is first how to note the main scale reading. 0 of the Vernier scale. To which reading in the main scale it coincides. So this 0 of the Vernier scale may coincide with particular reading in the main scale or in between 2 readings. Because this is a minute calibration, very close to calibration, you have to use a lens system and you have to note it. Now you see 0 of the Vernier scale coincide with which reading of the main scale or lying between which 2 reading that you have to note it. Now in this diagram it is lying between 12.15 and 12.2. So which reading you have to take means which is the lowest value that you have to take. Suppose 0 of the Vernier scale is coinciding exactly with the 12.15 means you can take it as 12.15. But if the 0 of the Vernier scale is between 2 readings in the main scale, between the 2 readings in the main scale, which is the lowest value, that is the main scale reading. So main scale reading according to this figure is, main scale reading is 12.15 centimeter because it is in centimeter. So 12.15 centimeter. So this is, you have to convert it into meter. So or 10 power minus 2 meter. Then you have noted the main scale reading. Next is Vernier scale coincidence. Among the 50 divisions, 1, 2, 3, 4, 5 like that, 50 divisions are there. Among the 50 divisions, leave the 50th division. Definitely the 50th division is coinciding means it will go to the next reading in the main scale. So leave the 50th division of the Vernier scale. Among 1 to 14, 0 to 49 division, any one of the division will coincide with the main scale reading. That you have to, with the lens, you have to see. See, each division is slightly away from the main scale reading. Each division in the Vernier scale is slightly away from the main scale reading. But one of the division may coincide with the Vernier scale reading is coincide with the Vernier scale division will coincide with the main scale reading. Each division in the Vernier scale is slightly away from the main scale reading, but one of the division among 0 to 49, one of the division may be coinciding with the main scale reading. Suppose for example here 23rd division, just for your understanding I am telling. 23rd division, 0 to 49. Suppose 23rd division is coinciding. Rest of the divisions are slightly away from the main scale reading. So now, now Vernier scale coincidence, which is in division. So now 20th division, 23rd division is coinciding. So 23. Now next is Vernier scale reading. How to? So main scale reading, Vernier scale coincidence. Now Vernier scale reading is nothing but Vernier scale coincidence into least count. Least count, while I am demonstrating that, I have told you, anyway I will tell you the least count of traveling microscope. Least count of traveling microscope is equal to value of one main scale division divided by number of divisions in Vernier scale. So value of one main scale division is what? Each 1 centimeter is divided into 20 main scale division. So value of one main scale division is 1 by 20 centimeter, that is 0.05 centimeter divided by number of divisions in the Vernier scale, 50 divisions. I have told you. So 0.001 centimeter. Now Vernier scale coincidence is 23 into 0.001, which is in centimeter, or 10 power minus 2 meter. Now that is equal to 0.023 centimeter or 10 power minus 2 meter. Now total reading. Total reading is equal to main scale reading plus Vernier scale reading in centimeter or 10 power minus 2 meter. That is 12.15 plus 0.023. You will get 12.173 centimeter or 10 power minus 2 meter. Like this you will get a reading. So in this traveling microscope you will get reading in 3 decimal point. The least count is in 3 decimal point.